In this video, we're talking about the precise definition of the limit, which is also called the epsilon delta definition of the limit, and we've been asked to use the precise definition of the limit to prove this limit equation. So we've been told that the limit as x approaches -3 of this function here, 7x minus 9, is equal to 30. So we already know the value of the limit, and intuitively this should make sense to us because the easiest way to evaluate a limit is with substitution. And if we say that x gets really close to -3, in fact, if x is equal to -3, if we plug -3 into this function here, what we see is that we get 7 times x minus 9, or if x is -3, we get 7 times -3 minus 9. 7 times -3 is -21. -21 minus 9 is a -30. And so we've already been told that the limit as x goes to -3 of this function is -30. And in fact, if we use substitution to evaluate the limit, we can see that that is in fact true, that the value of this limit is -30, which means that when we have the function f of x is equal to 7x minus 9. This is our function right here, f of x. When we take the limit of this function, as x gets really close to -3, the value of the function, the value of f of x here, is going to get really close to -30. And in fact, because the substitution works here, when x is equal to -3, f of x is equal to -30. So we can use substitution to see that that's true, but how do we use the precise definition of the limit to prove that it's true? So let's talk for a second about the precise definition of the limit. The precise definition of the limit relates these two inequalities, and I've kind of simplified the definition here. But it tells us that if this absolute value of x minus a is greater than 0, but also at the same time less than delta, so this here, keep in mind, is delta, that implies that the absolute value of f of x minus L is less than epsilon. So this Greek letter here is epsilon. So how do we use this theorem, this precise definition of the limit, to prove that this limit is true? Well, basically all we have to do is find a relationship between epsilon and delta. If we can find a relationship between epsilon and delta in the form of an inequality, then we can prove that this limit exists. So we'll come back to this particular problem in a second, but let's talk about what this theorem is saying here. Let's start with this epsilon piece here. Epsilon is the distance that we can move away from L. So we've got this graph here, and we've made up a linear function. This f of x function has nothing to do with the problem we've been given. We just have this linear function, and we're going to call it f of x. And we know that for f of x, the limit as x approaches a of this function here, f of x, is equal to L. In other words, as we get really close to a along the x-axis, as x gets really close to a, so we get closer and closer to it, we can be on either side of it, but as we get really close to this value, x equals a right here, then the value of the function gets really close to this value L. So the closer we get to a, coming in this way, or the closer we get to a coming in this way, the closer we get to L coming in this way. And that should make sense because if we sort of trace our finger along the graph and we get closer and closer to this vertical line here, x equals a, we can see that our function's value gets closer and closer to this line here, y equals L. And as long as there's no discontinuity at this exact point, if we just plugged a into our function, we took f of a, let's say that a is 4, right? We have x equals 1, 2, 3, and 4. So let's say that this point here is x equals 4. If we just plugged 4 into our function, the value we would get back is L. So the value of the function at 4 is L. So when it comes to the precise definition of the limit, the easiest way to think about it is as a question. So if we say that epsilon is a distance that we can move away from L, so let's go ahead and indicate that this point right here along the y-axis is the value of L, and we're going to move away, let's say maybe this distance right here. Maybe that's about 1 unit here, and we're going to move away 1 unit this way to this point right here. In other words, we can move a distance of 1 unit away from L along the y-axis. We can move down 1 unit or we can move up 1 unit. So we're sort of defining epsilon as 1. We can move away from L 1 unit in either direction. If we sort of set that parameter for epsilon, if we set that as a limitation for ourselves, we can only move 1 unit away from L in either direction, then the question is, how far can we move away from A along the x-axis and still be within that range? So in order to figure that out, what we want to do is carry over the edges of our epsilon range. So if we draw a perfectly horizontal line from the top of that epsilon range over to our graph until we hit the graph, and then we draw a line down to the x-axis like this, and we do the same thing for the bottom here of this epsilon range. So we draw a perfectly horizontal line over to the graph, and then we come straight down until we hit the x-axis. What this gives us then is these 2 points right here. So this point here and this point here, where those lines meet the x-axis. And so we can see just by looking at this diagram that if we start here at this point A and we move this direction this far, as long as we don't cross this line or go outside of this point, and same thing here, we can move all the way out this way, as long as we don't cross this line or go to the left of this point, we know we're going to be inside of this epsilon range. Well, this distance here is the distance delta. So if we go back to our definition here, what it says is that we have this absolute value here of x minus a. So let's pretend here that x is 5. We know that a is equal to 4. This x value here is coming from 5 right here. So if we pick x equals 5, then here in our definition we're going to get 0 less than the absolute value of 5 minus 4, since a is 4, the value here that we're interested in, less than delta. And if we simplify, 5 minus 4 is 1. The absolute value of 1 is still 1, so we can say 0 less than 1 less than delta. Well, this 1 right here, this 1 value right here, that's the distance between a, which we said was 4, and the x value we picked, which we said was 5, this distance right here. That's a distance of 1. So if we say that that distance is less than this delta value here that we already indicated, this length right here between a and the edge of this interval, this dotted green line here, if this distance between x and a is smaller than delta, then that implies that this inequality is also true. And this inequality says that the distance between this f of x value and L is going to be less than this entire epsilon distance. In other words, and this is really what it comes down to, as long as the difference between x and a, this distance right here, as long as that is smaller than delta, then I know for sure, and I can prove with this definition, that the difference between the value of my function and L is going to be less than this epsilon value that I defined in the beginning. And then if I flip that around, what it tells me is that if I continue to pick smaller and smaller values of delta, that the value of epsilon will also get smaller and smaller, which just says that as I get closer and closer to a, my function's value is also going to get closer and closer to L. So how do we use that definition to prove that this equation is true? Well, we use these two inequalities here. So this a value comes directly from -3 right here. So instead of 0 less than absolute value of x minus a less than delta, we're going to plug in for a, we're going to plug in -3. So we're going to get 0 less than the absolute value of x minus a -3 when we plug -3 in for a, less than delta, and now we'll simplify this. So we'll get 0 less than the absolute value. X minus a -3 is x plus 3, so we get x plus 3 less than delta. So we already plugged in -3 for a. Now into the other inequality, we're going to plug this function here, because this is f of x. We're going to plug this in for f of x, and we're going to plug in -30 for L, because what this limit equation tells us is that the limit of this function, 7x minus 9, as we approach -3 is equal to 30. So the limit is -30, so L is going to be -30. So let's go ahead and plug these two things into this other inequality here. So we're going to get the absolute value of f of x, which we know is 7x minus 9, minus L, or minus -30, and that's going to be less than epsilon. Now we want to simplify this, so we're going to say absolute value 7x minus 9 minus a -30 is plus 30, less than epsilon. -9 plus 30 is going to give me a positive 21, so I'm going to get 7x plus 21 less than epsilon. If I factor out a 7 from the left-hand side, I'm going to get 7 times x plus 3 less than epsilon. And then when I have two things multiplied together inside of absolute value brackets, I can separate them into their own absolute value. So we can say absolute value of 7 times the absolute value of x plus 3 less than epsilon. Well, we know that the absolute value of 7 is still just 7, so we can call this 7 absolute value x plus 3 less than epsilon. And now if we divide both sides by 7, we get absolute value of x plus 3 less than epsilon over 7. Now here's where we're going to draw our relationship between delta and epsilon. We started with these two inequalities in the definition, and we're left with this inequality and this inequality here. Those are the two that remain after we've plugged in a, f of x, and L. What we want to notice here is that we have the same value in each inequality. We have this absolute value of x plus 3, and we have absolute value of x plus 3. Since we have the same value in both inequalities, what we can do at this point is define a relationship between the right sides of both inequalities, delta and epsilon over 7. So what we can say in conclusion is that if we pick any value for epsilon that's greater than 0, so in other words, if we choose any positive value of epsilon, it doesn't matter what it is, we just want to be able to move any distance away from this point L. If we choose any positive value of epsilon and we want to stay within this epsilon range right here, we want to stay inside of these boundaries, then we have to choose a delta that is less than epsilon over 7. So we set this value here, this right-hand side delta, less than this right-hand side epsilon over 7. And the fact that we're able to state a relationship between delta and epsilon proves that this limit equation is true.